Now we turn to the hash table as an abstract data type. Let's list the operations it promises and the rules you must follow. This table is the hash table contract. The first column names the operation. The second column says what it means. The third column is the precondition, which is what you must guarantee before you call it. C does not check any of it for you. Creative M starts a new table with M empty buckets. It has no precondition. You can always make a fresh table. Insert of T, key, and value stores the value under the key. If the key is already there, it overwrites the old value. Its precondition is this: the key must be hashable and it must be comparable for equality. Search of T and key returns the value stored under that key. If the key is not there, it reports not found. It has no precondition. Two more operations. Delete of T and key removes the key and its value. If the key is absent, the table is simply left unchanged. No error. Update of T, key, and value overwrites an existing key's value. That is the same work as insert, so in practice, the two usually share one piece of code. Every operation on the list needs two things from a key. First, the key must be hashable, meaning a hash function exists for it. Second, the key must be comparable for equality, the equals equals operator for integers or the string compare function for strings. And here is why the second one is not optional. Hashing alone cannot tell two keys apart once they land in the same bucket. The hash gets you to the right bucket. The equality test is what finds the right key inside it. An invariant is a rule that must always stay true. If one ever breaks, the hash table stops working. The left column names each rule. The right column says why it matters. First rule: every stored key sits in the bucket that its hash and its probe sequence point to. If a key sat somewhere else, search would not know where to look for it. Second rule, for chaining: each key appears in exactly one chain and only once. A duplicate would make search ambiguous because it would not know which copy is the real one. Third rule, for open addressing: no live key sits past a gap it should not have skipped. Search stops at the first truly empty slot. A live key beyond that empty slot could never be reached. This third rule is the reason tombstones exist, which we will meet in a few slides. When you delete a key, you must not leave a plain empty gap in the middle of a probe path that another key still needs to cross.